So following the product rule, a very used rule, and the last one that we'll talk about in this series is the quotient rule. So very similar concepts. We have two functions. In this case, one function divided by another function. And the quotient rule tells us we need the derivatives of each of them individually. And then what we do is we take the derivative of the numerator, right? F of x is the numerator, times the function of the denominator, so f prime times g, subtract the numerator, f, and the derivative of the denominator, g prime. Then divide that quantity by the functions squared, right? So f prime times g minus f times g prime divided by g squared. So just like we did for the product rule video, we'll take a couple examples and show some graphs. We'll take one example, I think, of something we know the solution of, just so that we can show that it does work. And then we'll take an example where we use both the quotient rule and the product rule to show that both give us the same solution in two different methods. Here we have a problem that we know the solution of, right? Y equals x squared. We know this is going to be 2x. The derivative of x squared is 2x from the polynomial rule that we set up earlier. But we can change this into a two-function system, right? X cubed divided by x. That's the same thing as x squared. So let's try to set this up. So x cubed is going to be my f of x in my numerator. X will be my g of x. And then we'll take the derivatives and plug it into this formula. All right, so I have x and x cubed, right? F of x and g of x. So if we graph it, this is not too interesting, but x squared is what I'm focused on, right there. We can visualize the derivative of each of these terms, right? Derivative of x is just going to be 1. Derivative of x cubed is going to be 3x squared. So we take those derivatives, and then we plug it in here. So I'm going to have f prime, which is going to be 3x squared, times g of x, which is x. So 3x squared times x. Subtract f of x and g prime of x. F of x is x cubed, g of x is 1. And then we divide that by g squared, which is x squared. So we're 3x squared times x minus x cubed times 1 divided by g of x squared, which is just x squared. We can clean this up. So my numerator is going to be 2x cubed. My denominator is going to be x squared. So I get my 2x that I expected to get, right? So we can see that the quotient rule worked for this scenario. We can graph the numerator and denominator here and the final derivative in dashed lines here, right? So 2x in dash line, 2x cubed in blue, and then x squared in green. And we've done this a number of times, so we can recognize that this is the derivative of this term here, right? So negative slope coming down, 0 slope, right? That's reflected by the dashed line crossing the 0 right there, and then a positive slope going up, and that's reflected by this constantly increasing linear 2x curve. Okay, so let's take a look at some more examples. All right, so in this example, we see a numerator with a constant. Oftentimes, we'll see something like this, and you can simplify the quotient rule and just get rid of this first term. And this is also a good way to check, because it's very common for students and even for me to forget the order, right? That it's f prime times g minus f times g prime rather than the flip of this. You know, if you write g prime times f minus g times f prime, you're going to have a sign error in your system. So how do you remember which one it is that this term goes to 0, and you're going to have a negative sign in front of your derivative components. So let's work through this problem, and let's see that this goes to 0. And I suggest that you use that to your advantage to help you memorize the quotient rule. So a lot of times I'll be like, all right, I need to use it, forget which order it is. I'm just going to think about the derivative of 1 over x as a reference point and just take a look at the signage. In this case, we have 1 over sine x, but essentially it's the same concept, right? So my numerator is the function y equals 1. That's my f of x. My denominator is sine of x. All right, so let's graph these. So I have my oscillating full function here, flipping back and forth from having a maximum and having a minimum. And then I have my numerator and denominator, my constant 1, and then my oscillating sine x curve here. And we can kind of see some interesting ideas here, right? So we have minimum terms when we have the max of sine of x, right, at those peaks, because it's 1 over the peak of sine of x, right? So 1 over 1. And then when sine of x is positive, we're going to have a constantly increasing value for 1 over sine x. And when sine x is negative, we have constantly starting at a very low, right? As it's closer to 0, it's infinity, right? So we have these oscillating vertical asymptotes. So let's take a derivative of g of x and f of x. So we get cosine x for the derivative of sine x and 0 for the derivative of 1. And if we plug these values in to my quotient rule, you see you get 0 times sine x. So this term goes to 0. So you always will get this if your f of x is a constant. So if the numerator is a constant, you will always get a 0 for f prime. So you don't even need to think about this term. You can just get rid of it and just focus on negative the original numerator function times the derivative of the denominator function divided by the denominator squared, right? So if I do that, f is 1, g prime is cosine, and then gx squared is sine x squared. So this term goes to 0. We get negative 1 cosine x, and then we get sine x quantity squared. So we can look at this as your numerator, your new numerator is negative cosine x, or the derivative numerator is, and then the denominator is sine squared x. So if we graph it all, the dashed red line is my full function derivative, and then there's my sine squared x in green. It will never cross the x-axis, and then negative cosine x in blue here. If we graph the original function, 1 over sine x, and the derivative negative cos over sine squared, here's our graph. So we can take a look at this to make sure it makes sense, right? So the dashed line is my derivative. So the quick thing I would check is first your minimum maximum and make sure your derivatives are crossing the x-axis at those points, right? So here's a maximum, I'm crossing the x-axis. Here's my minimum, I'm crossing the x-axis, and it is oscillating in that way. Then we could look at when your full function is approaching, like the slope is getting larger and larger, right? In either way, right? It's getting larger and larger positive, and so your slope is reflecting that as well. Over here, it's getting, I guess, larger and larger negative value, or smaller and smaller. And then the slopes are reflecting that as well. So it is conceptually following what we would expect the slope and oscillations to look like, right? So when the main point here is if you have a numerator with just a constant 1, you can immediately eliminate this first term, the f prime g term, because you know f prime is going to give you a 0 value. All right, so we're going to solve this problem first with the quotient rule, and then I'll show you that we can also solve this problem with the product rule that we saw in the previous video. And we'll show you get the same solution with 2 different methods. And a lot of times that is an option for you. So it's good, right? Because it also confirms that both rules do work if they can validate each other. All right, so we have natural log x in my numerator, so that's be my f of x, and x in my denominator, that's my g of x term. And so my full function is kind of a modified form of the natural log, right? So in red is my natural log x over x, my full function. In green is my natural log x, and you basically see it, the full function is kind of a squashed down version of natural log because it's natural log divided by x. So as x is growing, the natural log growth is suppressed. And so now we can apply the quotient rule, right? So derivative of x is just 1. Derivative of natural log x, we see, where did we have it? Oh, right here, 1 over x, right? And so now I can plug it in here. So f prime is 1 over x, g of x is x. So 1 over x times x minus f of x times g prime x. F of x is natural log, g prime is 1. And then we divide that by g squared, or x squared. Okay, so that's what we have here. There's a f prime, there's my g of x, there's my f of x, there's my g prime, and then there's g of x, quantity squared. So I simplify this. 1 over x times x is just going to be 1. So 1 minus natural log x is my numerator, and then x squared is my denominator. So if we graph this, in red is my full function. It's a slightly modified form, again, similar to the natural log from the full function here. The derivative in the numerator section, 1 minus natural log x here, and then my x squared. If I graph the full function and its derivative, we can compare it. Oh, yes. I want to use the product rule. So how would I use the product rule? Well, the product rule is basically saying I'm taking two functions and multiplying them together. So I would just need to identify different functions. So instead of saying natural log x and x, I can say natural log x and 1 over x, or x to the negative 1. That'll be the same thing, right? So if I treat it like this, then I could say natural log x times the derivative of x or 1 over x, plus the derivative of natural log x times 1 over x, right? And so that's what we do here. So derivative of natural log x is 1 over x times 1 over x plus natural log x times the derivative of 1 over x, which is negative 1 over x squared, right? You see how that's the product rule. All right, and then we add these together. This was 1 over x squared plus or minus natural log x over x squared. So 1 minus natural log x over x squared. It's the same thing. And if we graph these, we have in the solid line natural log x over x, and we see we have a large, starting at a very large positive slope and then slowly decreasing and then reaching a near asymptote right there, so near constant, right? So then that's reflected by the large derivative function initially, then decreasing to 0. So this conceptually, again, makes sense. So we'll take a look at one more example problem to solidify our understanding of the quotient rule. So this is an example problem of 1 over e to x. So a couple things that we note here. First, we have a numerator of 1, a constant. So we remember from a couple examples ago, we can get rid of this first term here. And the second thing is we know the solution to this, right? Because 1 over e to x is the same thing as e to the negative x, which we know the solution here. So I don't even need to work this out, and I know the solution because we derived it a few videos ago. But let's work it out using quotient rule just so that we have something else to compare. So if I worked out the full quotient rule, f of x would be 1, g of x would be e to the x. Again, you could do the product rule on this one, right? You could treat this as 1 times e to the negative x. It'd be kind of a pointless one. That's why I'm not going to do it, because that's basically taking the derivative of this term. That's all. But let's work out this piece. All right, so if I graph these. I have 1 over each of the x in red here, and kind of basically mirrored across the y-axis, each of the x in blue, exponential growth, and then the constant 1. So then if I take the derivative of e to x is just e to x, derivative of 1 is 0, right? So then when I plug it into my quotient rule, I know this term is going to go away. I know this term is going to be negative e to the x, and then it's going to be e to the x squared, right? So then I'll get my negative e to the x over e to the 2x, or e to the x quantity squared, same thing, right? So my final solution is negative e to the negative x. Well, you can also see that if you take the derivative of the negative e to the negative x, you get e to the negative x. And so it will keep going back and forth. So if we take a look, all right, so here are the graphs of all the derivatives and the numerator and denominator. But if I look at the derivative of e to the negative x, my full function, and negative e to the negative x, my derivative, you'll see that they are the derivatives of each other, which is not always the case, right? So the full function starts off with a large negative slope, right? And it gets shallower and shallower until it goes to 0. Right here, this is the derivative of it, right? So it starts off a very large negative value, gets smaller and smaller until it reaches 0. So it's reflective of that. Then if we try to kind of flip the idea, if you look at the slope of the derivative, right? Initially it has a very large positive slope. Then it gets shallower and shallower until it reaches 0. And then if we look at the full function and think about it as the derivative of the derivative, or a second derivative, then it's a very large value, which is what we said, large positive value, and it gets smaller and smaller until it reaches 0. So you can see the unique behavior of each of the x, each of negative x, that it's a derivative of itself, or a second derivative of itself, and it just goes back and forth in that way. Knowing that can help us with some more complicated application problems where you do see each of the x or each of negative x. Sometimes there might be offset because it might not always be a decay value like it is here going to 0. It could be a decay value to a constant, 5 or something like that. We can easily manipulate the exponential equation to accommodate that offset with the asymptote just by adding a term to it. So we'll look at some applications in future videos where we see this kind of manipulation show up and try to give it some physical meaning. And again, this is important for tuning, just like when we looked at the trig functions and looked at the sine oscillation tunability.